All right, check it out. In the spirit of minimum viable products, this is not going to be perfect. All right, we're going to do both chalk talk and screen display. So today we are at lecture 3. The date is 2020 9/8. So we're going to cover some concepts related to time series. So you've all seen time series plots before. You don't need to write this, but for example, you might have time here and you might have some variable that varies across time. For example, stock prices or temperature or things like that. So, all right. The first thing we need to understand is, the first thing we're going to do today, in fact, is the following. It is the race to the first data visualization. Race to first data viz. Now, this is a great principle that I try to follow in my life whenever I'm stuck on a project. It's like, oh no, what do I do? How do I do this analysis? Well, it's like, boom, I try to make the first visualization. So using that temperature data, all right, we are going to make a time series plot using that same data. So let's go over here. This is code that I've shared on the webpage. These are various packages that you'll need to load. Now I've got a large pipe here, and you should all be familiar from this from 192. Now I really recommend that you break down these steps piece by piece to see what's going on at each step. So, for example, here you can see, oh, there's a lot of data. And in fact, it was collected at a US weather station in Front Royal, Virginia at different dates. Now, we do a little date processing over here. So let me highlight that and press on my Mac Command Enter, on a Windows computer, Control Enter, all right? But the main thing we're gonna do is, for each month, we are gonna take two values: the average daily maximum temperature here and the average precipitation. So for example, on this date here, and my screen's unfortunately a little too small, the maximum temperature in January was 63 degrees. So for each month, we're gonna take the daily maximum temperature and average them. What do we have here? Oh, okay, that makes sense. We have, for example, for November 2010, the average maximum temperature was 59.6 degrees Celsius. And here is the precipitation. But here's one more thing you need to understand is we're going to have to convert this to a TS-IBL, which is a time series tibble, or a special type of data frame. So if we run all this, it's the same thing, but notice this metadata here, folks. 1 month. It's saying that the increments or the frequency of the data is 1 month. So the first data viz that we have is, after we've converted our data frame into a TS-IBL data frame, we're going to use the autoplot function. There we go. What do we have? We have the monthly average T max temperature. And oof, I should really label my plots. But let's go back over here to our notability. So what we have here, what do we have? That is number 1, FPP, chapter 2.2, figure 2.1. Now, what do I mean by FPP 2.2, figure 2.1? Let me jump back to my my computer over here. You can see that, okay, I'm talking about chapter 2.1. Chapter 2.2, figure 2.1. So I made the equivalent figure as in the book, but now using our data. Let's go back over here. So note, constructed from a TS-IBL. Just remember, folks, what does that mean? That is a time series tibble or a time series data frame. But remember that in the metadata, it said the frequency is month. All right, let's go back to R. All right, so here is, for example, that kind of makes sense, right? That for these periods here, I think that's July, all right? We have these peak max daily maximums of about 90. I think that's about 30 degrees Celsius, all right? And then we have these dips. So here is a time series that we can analyze. The next plot we're going to look at is over here, and it's based on 2.4, figure 2.4. This is a seasonality plot where we're going to separate out based on seasons, or basically things that repeat yearly, specific trends. So let's go over here. If we run that, oh, check it out. Now it splits out January, February, March, December, but now by year. So let's go back to our notes here. All right. Number 2. This kind of plot is called and I've already forgotten, it's called a seasonal plot. This is FPP 2.4, figure 2.4. This allows you to see the repeats by season. Allows you to viz repeats by season. All right, cool. So that's called a seasonal plot. The next plot we're going to look at, let's jump back to R. This is now FPP figure 2.5, figure 2.5. This is based on the reading here. This is now called a seasonal subseries plot. This is just a different way to slice up and cut up that data. So here, okay, we're going to look at it for each month. What were the different prices, in this case, for a particular drug? But in our case, this is a seasonal subseries plot. Okay, those are the different temperatures, but now sliced a different way. We see that, okay, in this bottom right corner, all right, for each month, we get an idea of what that temperature is, and we see the peaks are in July, and the valleys are in December and January. So, let's go back to our notes. 3. What were these types of plots called? They were called seasonal subseries plots. Seasonal subseries plots. And think of this as a different way to slice up data to view trends. All right, so hey folks, data visualization is really important. But now we're going to cover another different type of concept of lag. All right, so let's go back to R over here. This is now FPP3 2.7 figure 2.16. So again, that is in lag plots. Here, now, it's not going to be so obvious. I'm not going to use this example for lag to illustrate what this plot is. Let's go back to our temperature data. All right. What do we have here? Remember, our units were month. So for example, these plots here show the correlation for the, or just a plot of the association between, let's say, the weather for all the observations in January with all the observations in 1 unit previous, December. you see here, oh, okay, they're sort of weakly correlated, right? Because if it's cold in January, it's going to be cold in December. But now, let's take a look at a lag of 6 units. Well, over here, we see that now there's basically an inverse relationship, right? Because 6 months is exactly what? Half of the year prior. Basically, it's the opposite season. So we have a negative relationship right there. But then, what does a lag of 12 months correspond to? For example, for all observations in January, let's take a look at all observations for 12 months prior to that, and we see that everything fits on a line like that. So that's the concept of a lag. Let's go back to our notes here. So lag plots. So let me just see what the name of these things are. These are called lag plots. Lag plots show relationship of variable with same variable lag units ago. So in this case here, in R, we were looking at units of months. So now we saw that there's an obvious relationship between, for example, 6 months ago, there's a negative relationship. Actually, let me go back to R. 6 months ago, we see that there is a negative relationship between the daily maximum average temperature, and we have a positive relationship down here. We have time for one last plot over here. We can also get these values numerically. And what this is called an autocorrelation function plot. Now, you might be saying, whoa, there's a lot going on over here. But really, folks, it's actually quite simple. For a lag of 1 month, the correlation coefficient, which you must have seen in intro stats, is quite high. It looks like it is about over 0.75. But then for a lag of 6 months, that correlation is actually negative, maybe 0.75. Really, the temperatures are inversely related. But then when we come back to a full cycle of a year, we have 12 months. That correlation is as high as can be. It's not quite 1, but maybe it's about 0.8. So let's go back over here and write that down. Oops, so I'm sorry, I didn't write down the figure numbers here. So this should be, what is this? FPP. Let me write this down. 2.5, figure 2.5. Over here, number 4, that should be FPP 2.7, figure 2.16. And last but not least, number 5, we have ACF, which is autocorrelation function plots. Auto means self in Greek. So the idea is we are looking at the correlation of a variable with itself. Look at correlation coefficients of variables with itself, lag units ago. And this is FPP 2.8, figure 2.17. All right, there's our minimally viable product. I'll be soliciting feedback from you all, but I think this is good enough for a first pass.